Hello, this is Time Dilation by Jared. Now before I get into time dilation, I'd like to talk to you about the postulates of special relativity, or the rules of special relativity. Now, in Albert Einstein's 1905 paper, called The Theory of Special Relativity, he outlined two rules, which as long as they hold true, a multitude of other things can be derived from it. These can include length contraction, and in the case of this video, time dilation. These rules are: 1. The laws of physics are the same in all inertial frames of reference. 2. The speed of light is constant at a velocity of roughly 3 times 10 to the 8 meters per second in all frames of reference. Now, what is an inertial frame of reference though? Well, the best way to think of a frame of reference is being similar to a point of view. In the case of you, your frame of reference would be the world that you see around you, the environment that you're surrounded by, your perspective. In the case of a tree, its frame of reference would be the jungle that surrounds it and the grass at its feet. Frame of reference is basically point of view. Now, an inertial frame of reference is a frame in which Newton's first law, the law of inertia, is valid. And it is a frame that is at rest or under a constant velocity. This means you sitting in a chair at 0 meters per second, completely at rest, are in an inertial frame of reference. But at the same time, a sports car traveling at 30 meters per second is also in an inertial frame of reference. In fact, both these events are in the same frame of reference. From the point of view of the car, or frame of reference of the car, it is actually at rest, while the person sitting down would be moving 30 meters per second. This idea of relativity isn't a new concept. In fact, it is actually derived from the work of Galileo and Isaac Newton. Galileo, who originally conceived the idea, and Isaac Newton, who helped develop the idea. So, here are just the basics of Galilean-Newtonian relativity. Let's assume that you are standing on the Earth, and that there are two spaceships passing by. One, a large spaceship moving at 10 meters per second, and two, a much smaller spaceship moving at 50 meters per second. Both are moving towards the right. Now, to you, you would think that the Earth is completely at rest. However, if you are moved to the large spaceship, you will see the Earth moving backwards, or to the left, at 10 meters per second. Now the large spaceship will seem to be moving at 0 meters per second, because it is at rest relative to you. And the small spaceship will now be going 40 meters per second. Again, if you move, the Earth will now be traveling towards the left at 50 meters per second, and the large spaceship will be traveling to the left at 40 meters per second, and the small spaceship, which was incredibly fast, now seems to be traveling at 0 meters per second relative to you. This means that there is no such thing as absolute motion, as everything is relative. So, if we consider Einstein's postulates, then if you are standing on the Earth, light from, say, the sun will still be coming towards you at speed c. If you are on the large spaceship, light will be coming towards you at speed c. And if you're on a small spaceship, light will still be coming towards you at speed c, because c is constant. Now, what can this mean? Well, let's consider car A and car B. Car A is completely at rest, while car B has some velocity v. As we know from classical physics, distance equals velocity times time. So, in the case of car A, the total distance covered by its headlights will be equal to c times t. But in the case of car B, its distance covered will be equal to c plus v times t. But how is this possible? Well, Einstein proposed that t must have to change. As you can see here, this is an Einstein clock. The Einstein clock works in this idea of two mirrors, upon which light, as indicated by the two yellow arrows, is bouncing between. So we've got David here, and he notices the clock moving with some velocity in the horizontal direction. He is a stationary observer. Let's let t equal the time from the clock, and let's let t dash equal the time observed by David from his own personal clock. So firstly, we have ct dash. This is the distance as observed by David to get from one plate to the other plate. Next we have ct. This is from the clock's frame of reference to get from one plate to the other plate. And then we have the third factor, which is vt dash. Now, what you may have noticed is that this is actually a right-angled triangle, which means we can apply Pythagoras' theorem. Ct dash squared equals Vt dash squared plus Ct squared. Now if we divide by c squared, we get T dash squared equals V squared on C squared times T dash squared plus T squared. Now let's make T subject. T squared equals T dash squared minus V squared on C squared times T dash squared. Now let's collect like terms. T squared equals T dash squared times 1 minus V squared on C squared. Now we can square root. T equals T dash times the square root of 1 minus V squared on C squared. And then we can make T dash subject, and this becomes the time dilation equation. T dash equals T times the square root of 1 minus V squared on C squared. Now this time dilation equation actually exists at all times. Whether you're going close to the speed of light or you're just walking down to the shops, you're always experiencing time dilation. But how come we never consider this when we're doing our physics equations? Well, it's often not necessary. Let's consider this Bugatti Veyron. Its speed is equal to 431 kilometers per hour, or 120 meters per second. Now, let's say we have a clock in the car and a stationary clock outside of the car. So we can use our time dilation equation here and note down that the only real part of this equation that we actually care about is the V squared on C squared. So 120 meters per second squared divided by C squared equals 1.6 times 10 to the negative 13. 1 minus 1.6 times 10 to the negative 13 is so incredibly small that it's not even worth thinking about. However, there are some actual examples of time dilation that exist in the real world. The best being the Global Positioning System, or GPS. All around the world there are about 30 satellites built for GPS, and at any point in time there are usually 4 or more satellites above you. Each of these satellites is sending a signal to your phone with a timestamp, so your phone can figure out where it is located. Now each of these satellites needs to consider time dilation when it's sending these signals to your phone. As with time dilation, the inaccuracy is about 10 meters, but without time dilation, the inaccuracy could be easily as large as a kilometer. Of course, this is also considering a second form of time dilation, outlined by Albert Einstein in 1915 in his paper The Theory of General Relativity, called gravity-based time dilation. Gravity-based time dilation works on this idea that the higher the gravitational potential, the faster the clocks run. While there's our version covered in this video, velocity-based time dilation, which works on the idea that the faster something goes, the slower its time is. So, let's consider velocity-based time dilation with a practice problem to finish off. David has come back to help us with our practice problem. He sees the spaceship. The spaceship is traveling at 0.2 times the speed of light. On the spaceship's clock, it measures a time of 4.9 seconds. Now, using the time dilation equation, what time does David measure on his own clock? Feel free to pause the video. Velocity, or v, is equal to 0.2 c, and t, or time, is equal to 4.9 seconds. So, t dash equals 4.9 seconds over the square root of 1 minus 0.2 c squared on c squared. Now, c squared on c squared is cancelled out, so it becomes t dash equals 4.9 seconds over the square root of 1 minus 0.2 squared. This gives you a total time on David's watch of being 5 seconds. So, the clock on the spaceship measures 4.9 seconds, while David's own clock measures 5 seconds for the same amount of distance. Thanks for watching. I hope you've enjoyed this video and learnt something from it.